Hi everyone, welcome back to another lecture for Phys 4250 or 8250, Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. We'll be continuing on with Chapter 6, Pulsed Lasers, for Friday, October 23rd. So if you remember what we discussed last lecture, we talked about how you need to have no net group velocity dispersion within a cavity in order to maintain ultra-short laser pulses. We talked about on Monday how you can make Q-switch lasers, which allows you to generate these really high power giant pulses, but those pulses are about 10 nanoseconds in duration. And although 10 nanoseconds sounds pretty fast, if you think of the Fourier transform of that, the bandwidth is extremely narrow. And so we looked at the index of refraction of glass, say, for example, and if something, if the bandwidth is so narrow, then the pulse doesn't really see a change in the index of refraction. And so even though it's a pulse, a Q-switch laser, you don't really have to worry about dispersion that much. However, if we're trying to get mode-locked lasers, which we'll be talking about today, you need to worry about dispersion. You're very sensitive to dispersion. So we talked about this in Wednesday's course. If you have a 10 femtosecond pulse, which is definitely possible with a mode-locked laser, it passes through 1 millimeter of glass. After just a few passes, say 5 passes, you see that this pulse duration has increased by something like a factor of 5, and the peak intensity has dropped as well, because you have to have conservation of energy. So that means that this pulse spreads out, and eventually this doesn't really become a pulse if you have any kind of net group velocity dispersion. So what you need to do is have something that counters that group velocity dispersion. We also talked about what a pulse would look like. So with normal dispersion, we have, say this is a 4 femtosecond pulse or so, and it passes through, I think, about 50 femtoseconds squared or maybe 100 femtoseconds squared of dispersion, which would be about 3 millimeters of glass. This very, very short pulse would stretch out, and this is when you have normal dispersion, the red frequencies, the lower frequencies, the longer wavelengths, have a lower index of refraction in glass, as we have here. So the red frequencies have a lower index of refraction, they bend less spatially, and it means they're also delayed less in time, whereas the blue and the purple colors have a higher index of refraction, and these are dispersed later in time. So this is called an upchirped pulse, because in time you can see that frequencies are increasing, and so this is going up in an energy or up in frequency. Now, if instead you looked at this as a snapshot of a pulse, so say if you're looking at a pulse within the cavity, and so this is instead of a function of time, it's a function of z, then this pulse is flipped backwards, and that's because you have this relationship kz minus omega t. So when you draw a pulse like this, you now have to know if you're talking about this in terms of time or in terms of space. Both are correct, and they have this obvious relation, but if you show a pulse that looks like this and you say it's upchirped, well, that makes sense if it's in time, but if you show a pulse like this and you say it's upchirped, well, you have to specify that this is a function of z instead of the function position. Okay, so how do we get regions, or how do we have net zero group velocity dispersion in our laser cavity? So as we said, any material will have some kind of dispersion, will have something like this. Well, it turns out it's not just that the index of refraction is higher or lower, it's actually the second derivative of the phase with respect to omega, or of the k with respect to omega, is what gives us our group velocity dispersion. And so when we're in the visible, this is called normal dispersion, and that's because the second derivative of this is curved upwards. And then if you go into the infrared for, say, glass, you have this region here is anomalous dispersion, okay? And that's because this is curved downwards. So the second derivative of this, you can say this is slightly curved downwards. That means that you have anomalous dispersion. People in optics call it anomalous dispersion. If you look at through a resonance, you see when you're in this region here, this is normal dispersion, this is curved upwards. If you take the second derivative of this, this would be positive. And then just to the right of the resonance here, you have anomalous dispersion here. As I said, in Griffiths, he refers to this region as anomalous dispersion because this rapidly changes. But we would just call this in optics an absorption region, because light wouldn't really transmit through this anyways. Then after that absorption resonance, you then have this index of refraction is curved downwards again, and so you take the second derivative of that, and that would be negative. So this region here is anomalous dispersion. This region here is normal dispersion, and right here this is anomalous dispersion. And then if we kept on going, we'd have another resonance to the right of this, and this would also have a normal dispersion curve. We'll go through the math about this in class. In fact, I might have actually already gone through that in the last lecture. But what we want to talk about is regions of normal and anomalous dispersion, or showing that we can have both anomalous and normal dispersion. And if we have, our cavities just need to have net zero group velocity dispersion within the cavity. And so what we can do is if we have some material that has some normal dispersion, such as the gain medium, then we need to introduce some material that has anomalous dispersion in that same region, and it has to match fairly closely. On the assignment for the graduate students, you can show that a prism will have can have net anomalous dispersion if you set up the geometry correctly. So if you're interested in how people can do this, I recommend that you do that problem. But the net result is that if we have a cavity with net zero group velocity dispersion, we can have all of the modes, or we can have this pulse rattle around without significantly changing shape after each round trip, and so that allows us to keep this mode in this pulsed laser intact. And so what that means is that all of the frequencies end up being in phase, and this pulse, by maintaining its shape, locks all those frequencies in phase, and so that locks all of the modes, which are all the frequencies of the laser, and hence called mode locking. Okay, so in order to have a mode locked laser, you assume that there's no net dispersion in the cavity. In some cases you can have a little bit of net dispersion, and then it turns out that you have some optical nonlinearity in the cavity that compensates for that. And that's actually typically the case. You typically have some small net dispersion in the cavity, and then you have the nonlinear effect of the pulse propagating in the cavity is what makes it have zero net dispersion. So as I said, we'll for question 3 of your homework, we'll give you an idea of how to have a magical device that you can tune from positive to negative dispersion with a pair of prisms. But just looking at different materials, we can see that this is what it is for glass, but calcium fluoride has a different region where this anomalous and normal dispersion occur, and other materials, say like semiconductors like silicon, this is pushed to lower frequencies. I'll go through the math of what happens when you have a mode locked laser and what the consequences are. The upshot is that you get this equation that you have an even mode spacing of these frequencies. So the frequency spacing is given by, well, this is an omega, so it's going to be 2 pi times the group velocity divided by 2L. So if you remember before, we had for the Fabry-Pro cavity, for example, or for the Fabry-Pro Etalon, it was C over 2L, or for the laser cavity, C over 2L. This is instead the group velocity, Vg over 2L. So now we care about that group index of refraction, not the phase index of refraction, or the normal index of refraction that you're used to. And then the frequency, this is the absolute frequency position, and so the difference between two modes is going to be given by this constant here. But the absolute position of each of these frequencies is going to also have this additional term here that's dependent on the group velocity, dependent on the carrier frequency, and then the difference of the group velocity and the phase velocity. And this position here actually turns out to be sensitive to a lot of environmental perturbations. The phase velocity isn't so much sensitive to that, but it turns out when you have a laser pulse, you get some funny effects on the group velocity, and so it can be intensity dependent, it can become temperature dependent, and it can become quite sensitive to environmental perturbations. And this is actually part of my PhD thesis, so I'm quite familiar with how sensitive this can be. So the mode spacing, as I said, is going to be given by this omega rep. This is the repetition rate of the laser. The repetition rate of the laser, this spacing is going to be, as I said, instead of c over 2l, it's the group velocity over 2l, and then times 2 pi, because we're dealing with natural frequency. And then there's this offset frequency, is called this omega 0. This is offset frequency, which is given by the group velocity times the carrier frequency times the difference of 1 over the velocities. And so this is called the offset frequency. And within about 5 years, so my PhD supervisor was the one who actually first measured this, and about 5 years later, his boss actually got a Nobel Prize for this. So this is a 2005 Nobel Prize. So just as I was studying my master's, my supervisor's supervisor got a Nobel Prize for this development of high precision spectroscopy, including the optical frequency comb technique, and that's what this is. And we'll call it. And so the reason why it's called the optical frequency comb is because you can see from this visualization here, we have these pulses that happen in time. So this is the intensity. So we have this envelope function here. These things are spaced by the repetition rate, or in actual time, this is 2 pi divided by the repetition rate. And so then you have some pulse width of delta t. Then you take the Fourier transform of this, and because you have these pulses are so regularly spaced, you end up having this delta t here leads to this envelope here by the Fourier transform, right? So if you have a Gaussian pulse, say in time, then you get a Gaussian envelope in frequency, of course. But then because these pulses are so regularly spaced in time, it ends up being a convolution of the two factors. And so this regularly pulsed spacing leads to these regularly spaced comb elements. And so this is like, you know, a comb that you would use for your hair. And so that's why it's called a frequency comb, because this is a comb in frequency space. And the separation of these comb elements are given by this repetition rate. Now, we also talked about this offset frequency here. It turns out that if you look very, very closely at this, you go all the way down. This spacing is actually completely evenly spaced. But if you look all the way down to 0, it turns out that this isn't necessarily 0. And that offset from 0 is called the offset frequency of this omega naught. And this measurement of this thing here is what allows us to measure this frequency extremely precisely, and that allows us to know where these frequencies are extremely precisely as well. Or conversely, if we know these frequencies extremely precisely, we can then know what these frequencies are extremely precisely. And this is what led to the Nobel Prize, is that if you think about a cesium clock, so the atomic clock, this is kind of like the gold standard for time measurements, and this is what GPS is relied on. The cesium clock is something around 9 gigahertz. So what you could do is, if you take, say, this offset frequency might be at, say, 10 megahertz or something like that, and the repetition rate might be at 100 megahertz. Well, you take, the 90th comb element, and that gets you up to 9 gigahertz, and then you can precisely tune that comb element onto this cesium clock transition at 9 gigahertz, 8.9 something gigahertz, and you can exactly measure that atomic transition, and you would be able to lock these frequencies up here in the optical to something that you know is very precise down here. And because it's at 9 gigahertz, you can do this with electronics. So you lock that, and then that means you know all these comb elements up to, something like 5 petahertz or something like that, or maybe a few petahertz, with the precision that you have of this cesium clock. And there's no uncertainty in that cesium clock. It is given as a precise number because it's a standard. And so it means that all these comb elements here are given as some precise number. And so then that means that you can do extremely fine spectroscopy is when you tune these comb elements onto some transition. All right, so we want to finish off the week talking about amplification of short pulses, and this is exactly what I'm doing in my lab. So we have a mode-locked fiber laser that is frequency doubled, which we'll talk about in a few weeks, but it's an IR fiber laser, so infrared fiber laser, frequency doubled down to 780 nanometers. Then we put that into an amplifier system, and we get these amplified pulses. And what you can see is that you have this envelope of these pulses, and so each of these pulses, this is the repetition rate of the laser. So these things are separated by something like 120 megahertz or so. So they're separated by about 8 nanoseconds. So each time this pulse rattles around, it gets amplified. So you can see after, first time it gets switched into this amplifier, you get a little bit of energy, a bit more, 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 and then it starts to saturate. And this, these pulses don't really amplify much more, and you have two pulses of about the same energy, and then you switch out this pulse, and this pulse quickly gets switched out, and there's nothing left. And so I'll show you what this process looks like in this little animation here, and I might have to go to a little full screen mode. So what we have is, we have our laser oscillator here. So this is what I was talking about. We have a very weak mode locked laser here that's putting out pulse energy of a few nanojoules. It could even be less than that. So this spits out these lasers at very regular repetition rates at, as I said, 125 megahertz or so. That comes out, and it goes towards this big laser that's sitting here. This is the laser amplifier. We also have to have a Q-switch laser, which is sitting here. And this is a Q-switch laser, as we say, like we're pumping this with, some diodes or some other energy source. And we create this Q-switched pulse. And once this pulse is created, it comes also into this big amplifier. Okay, so Q-switch pulse comes in and excites this gain medium. So this pulse is quite long, as it says, it's something like 10 nanoseconds or so. And this now has huge, almost completely population inversion. Almost all the states are in N2 due to that Q-switch pulse. So that thing is going to last for quite a while. And then during that time, we have this weak pulse comes in, and we use this mirror here to switch in this pulse. Okay. We also have a mirror here it's called a dichroic mirror. It will allow green light to come in, but it'll reflect red light. And this is pretty easy to make mirrors with these kinds of coatings. Obviously, it's not like a silver mirror like you would think. It's actually, it'll be a glass mirror with a special kind of coating on it. But they're not that expensive. They're not that complicated to make. Okay, so this medium here has high population inversion. Almost everything's in N2. Now we have this weak pulse coupled in. Okay, that pulse rattles around, and through stimulated emission, it grows. So it can only rattle around if we take that mirror out, and this pulse rattles around many, many times, and as it rattles around, it becomes very amplified. Now, once this pulse is amplified, once that gain medium is saturated, or once that, basically it's saturated, we then put that mirror back in, and we switch this pulse out. And that pulse goes out some way, and then goes towards an experiment. Okay, so that is the basics of how we amplify ultra-short pulses. So in order to do that, we needed to understand where mode-locked lasers came from, because we need to have a mode-locked laser as the seed. It needs to be this weak laser that we want to amplify. We need to understand Q-switch lasers because we need to have really, really large pulse energies in order to have high population inversion in this crystal here, or in this gain medium here. And then we interact the two pulses many, many times, and that's what we get here, is each time that this weak pulse is interacting with this Q-switch pulse in that gain medium, we get this pulse growth. And then when we're at the peak of the pulse, we switch it out, and then we can work with these amplified but ultra-short laser pulses. Okay, and more technical details of that will be for somebody who wants to take on chirp pulse amplification, which I think I've assigned to somebody for their project.